10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
And liftoff of the Delta II rocket carrying...
On June 10th, 2003, a rocket took off from Cape Canaveral, Florida. Its lone passenger, an explorer on a one-way trip to Mars. His partner and identical twin followed soon after. They were born in California, endowed by a loving family with all the intelligence and skill humanly possible. But the explorers themselves are not human. They're robots, designed to go places and do things that humans cannot. To their creators, though, they're much more than machines.
First time I stood there next to the rover and watched it drive, it brought tears to my eyes. You know, I try to be this steely-eyed space explorer dude, but that one I just couldn't take it. It was just too much just seeing that. It was just, it's a phenomenal feeling.
For centuries, Mars was an omen of war and disaster. Today, it's a destination, but still dangerous.
We've lost about 50% of the missions that we've flown to the planet. It's a tough place to operate.
But the attraction is irresistible.
What's the single most important question that we're dealing with in space science? It's, are we alone? When we go to Mars, the nearest and most likely place that life might have arisen elsewhere in this solar system, what we were really doing is we're asking questions about who we are and where we came from. Maybe life evolved first on Mars and was knocked off the surface and carried to the Earth. Maybe we're all Martians.
If so, the proof is out there. But first, our explorers must survive the most dangerous part of the journey: landing on Mars. Tonight, Nova presents an exclusive behind-the-scenes chronicle of this great adventure. Mars, Dead or Alive, right now on Nova. It's the summer of 2002, and as usual, Steve Squires is on the road. He's a professor of astronomy from Cornell University in Ithaca, New York. In the past few years, he's logged almost 1 million miles, commuting to NASA's Jet Propulsion Lab, JPL, in Pasadena, California. This is where NASA builds spacecraft to explore the solar system. And at the moment, they're building 2 of the most sophisticated ever attempted. Twin rovers designed to unravel the secrets of Mars. These robots are the ultimate custom machines. No stock parts, nothing off the shelf.
This isn't General Motors, and we're not building pickup trucks. This stuff that you see here has never been built before.
A year before launch, the rovers and science instruments are bits and pieces of hardware scattered through a dozen different buildings. Steve Squires is the lead scientist and a driving force behind the mission. But the engineers will make it happen. More than 600 people at JPL are dedicated to MER, Mars Exploration Rovers. It's a demanding job with an unusual payoff.
I think it's easy to forget about the big picture when you start getting a little tired, a little burned out. Then you start thinking, why am I complaining? I'm going to work to drive a vehicle on another planet.
And not just any planet. Mars has tantalized us for centuries with a confounding mix of the familiar and the bizarre. Canyons miles deep and thousands of miles long. A volcano the size of Arizona and 3 times the height of Mount Everest. What water there is on the surface is frozen at the poles. There's evidence of more ice underground, but so far, not a drop of liquid anywhere. It's a frigid, almost airless desert of dust, wind, and radiation. Even for a robot, it's a hostile environment. But these rovers will be prepared for the worst.
They're going to be in a place where there's dust to get in the joints and the temperature goes through 100 degrees centigrade between nighttime and daytime. But this was the world that they were designed for. And so I think they're going to do okay.
The lure of Mars is the possibility that it wasn't always such a harsh and barren place. From orbit, we see ancient signs of water flowing across the surface, which could mean that Mars was once warm enough to be wet, and perhaps a habitat for life.
Just because there was liquid water there doesn't mean that there was life there. But we cannot imagine life without liquid water. So it's a necessary condition. I want to go to 2 places on Mars where we got good evidence that water was there, and I want to answer the question, was this an environment that would have been suitable for life?
The rovers will be field geologists reading the story of early Mars recorded in the rocks and minerals. Scientists on Earth will send instructions, but even at the speed of light, it will take 10 minutes or more for radio signals to reach Mars. So the rovers will have to be smart enough to make many of their own decisions, like how to navigate around hazards. They'll have high-resolution stereo vision to survey the landscape, plus an infrared camera called mini-TESS to locate minerals that formed in contact with water. More science instruments are on the robotic arm. There's a power tool to grind off the weathered surface of a rock. 2 spectrometers to sniff out what it's made of, and a microscope to examine its interior. It would be hard enough to make all this work on Earth, but to make it work on Mars will be extraordinarily difficult. And the engineers have just 12 months left to pull it off. Today, the instrument called mini-TESS is scheduled for a test. Because it can detect minerals that formed in contact with water, it may be the single most important instrument on the mission. They have to prove that this delicate piece of hardware is tough enough to survive the shocks and bumps it will experience on the way to Mars. It will be bolted to a slab of aluminum, which will then be struck by a gas-driven hammer, giving the instrument a severe jolt. Steve wants to make sure the engineers don't overdo it and break the instrument.
NASA ultimately holds me responsible for delivery of the scientific instruments on the payload. Now, I'm not an engineer, but I take my responsibilities very, very seriously. And if we break some hardware, it's going to be my neck on the line along with a whole bunch of others.
If we break this today,
$5 million.
Oh, $5 million?
And maybe no flight.
Let's make sure everybody's clear on what we're doing here. This is an irreplaceable flight unit.
Steve is worried because the point of this test is to prove that the instrument is tougher than it needs to be, what engineers call margin. But such tests are not usually done on the actual hardware going to Mars.
What we wish we had was an engineering model, which is another copy of the flight instrument, identical design, but not one that's going to Mars. Put it on the table, shock it, If it survives, means the design's okay, we don't have to do it with their flight units.
But at $5 million apiece, they could only afford to build two, one for each rover. A mistake here could cripple one of them and not leave enough time to recover.
That's what I'm trying to get at, is there's something we can break inside this instrument today that's going to cost 6 months to fix. Because if it is...
The engineer who knows the instrument best is Steve Silverman from Raytheon.
2 weeks to build a bean splitter up from scratch.
Squires wants to know if he thinks it can survive this severe jolt, or if they should insist on a less dangerous
2
test.
to 3 weeks of vibration test.
Do we do the test today?
And I called it a nemesis, and he said we should be able to survive it. Now, will we? I can't answer that one, Steve.
No, I'm not asking for a prediction. Okay, I'm asking for, I mean, it's a binary thing. Either we do the test today or we don't do the test today. What's your recommendation? Do we strap it to the table and shoot the thing off, or do we walk out of here with our instrument?
This is a tough one.
I know. We can cause all sorts of hell for a lot of people today, but we can't bring this whole project down. There's a natural, built-in creative tension between the science and the engineering, and ultimately, even though it gets people kind of riled up sometimes, it works to the benefit of the system. Okay, so your recommendation is?
I think we go. If the project is going to require a qualification test, we should do it now.
All right.
Because if we're going to break it...
If we're going to break it, we ought to break it as soon as possible. All right.
Finally, the moment of truth.
Come on, sweetheart.
No one will breathe easy until the results are in. Steve has to move on to other business, leaving the post-mortem to the engineers.
207. We're powering it up. The current's good. We're in business.
Current looks good.
Okay. Looks good. Current's good. Whew. So we survived the shot. All right. All right. Someone call Squires.
Hey Steve, wanted to give you the good news. We turned on mini test 1. It's working great. It survived the shock test, so we're pretty happy. So thought you'd like to hear it. Have a good flight. See ya. Bye.
He needs all the good news he can get. The clock is ticking, and Mars waits for no one. Every 26 months, the orbits of Earth and Mars bring the two planets to a brief, relatively close encounter, about 35 million miles apart. This is when missions must be launched, and the next opportunity is rapidly approaching. If they miss it, they may not get another chance, since it would cost millions to put everything on hold for 2 more years. And that's not all there is to worry about. Everyone remembers what happened the last time NASA tried to go to Mars. In 1999, a mix-up between English and metric units resulted in the loss of an orbiter. Just a few months later, a software problem caused a lander to crash. Mars is a graveyard for half the spacecraft ever sent there. But this time, they have to succeed.
I think the credibility of the Jet Propulsion Laboratory is at stake. I think that the credibility of NASA's Mars program is at stake. Hell of a lot of science is at stake. Last 10 or 15 years of my career is at stake. That's from a purely personal perspective. There's an enormous amount at stake here, and everybody realizes it.
10 months before launch, the engineers are feeling the pressure. They've been working around the clock to complete an engineering model of the rover. It has no instruments or solar panels yet, but otherwise it's identical to the ones that will go to Mars.
There are several thousand unique pieces of hardware, each one precisely placed, but never perfectly placed. It's really freaking hard.
Today is the first in a long series of tests to find out if the rover can perform its most basic functions.
Joel, whenever you're ready, go ahead and send the command. Command sent.
With that very first test, when you first see it happening, that technical part of your brain says, this has to work. That emotional part of your brain is saying, yeah, but what did you forget? You're not as smart as you think you are. And let's just say we never get past that fear until we're successful.
Wheels turn for the first time, and suddenly, Mars is much closer.
We just saw a rover move. It just came to life for the first time today in front of us. I mean, we're still under pressure, but we're doing it. You know, we're actually doing it. We're building stuff, we're driving stuff, we're taking pictures with the cameras, we're moving the arm and it's working. The morale right now is the highest I've seen it since the start of the project. We're just flying.
But the rover will have to get a lot more sophisticated if it's going to survive on Mars. And the biggest challenge will be the last 6 minutes of the journey.
During entry, descent, and landing, the rover is on its own. Okay, there is no back and forth between the vehicle and Earth. We've taught it what to do, and it does it, or it doesn't.
Atmospheric friction will slow the spacecraft from about 12,000 to 900 miles per hour. Then a parachute takes over. The heat shield falls away, and the lander descends on a long bridle. Now the rover inside keeps track of the altitude with radar. At 900 feet, a cocoon of airbags inflates around the lander. Just seconds before impact, reverse rockets fire to soften the blow. And then
they bounce, they bounce, they bounce, they bounce, they bounce, they roll, they bounce, they roll, they bounce. And that can go on for quite a while. I mean, we could roll and bounce like a kilometer.
The landing sites have been chosen with safety in mind.
But I can't tell you that somewhere in the middle of that there isn't a 5-meter tall, pointy, sharp rock that if you just happen to have a bad day, you land on, pop your airbags, and that's it. There is an element of luck about it.
Still without help from Earth, the rover has to unfold itself and call home to say, I've arrived.
Every one of those events is triggered by the computer. There are electrical signals, there are things that have to fire, and there's mechanical stuff that needs to work. Any one of those events fails, for whatever reason, and we're done. So there's a lot of things that can go wrong. And landing day, we're going to hope it all works.
Of all the things that could go wrong, the airbags seem the least likely to cause trouble. It's a relatively simple idea. Inflate a cushion around the lander and let it bounce. To test the bags properly, they have to duplicate the atmospheric pressure on Mars, which is less than 1% of the atmosphere on Earth. For the first test, they go to the world's largest vacuum chamber at a NASA facility in Ohio. When the chamber is pumped down to a near vacuum, they'll inflate the bag and drop it on a platform studded with sharp rocks to simulate landing.
We went out to Ohio and we were ready to do these, great and glorious tests and show everybody that, hey, things are going to work. Don't worry about this, guys.
So we're all sitting in a control room, and we've got a half dozen video cameras looking at all sorts of different angles. And everyone's sitting around saying, oh, I think we'll be good. And we drop. The airbag comes down, it hits the ramp, and as it's bouncing off the ramp, you see this huge gaping hole in one of the airbags. Whoa, what's happened here? This is unexpected.
It was a frightening moment. We all believed that we could make it happen, but all of a sudden we didn't know how it was going to happen, and we really had to rethink everything.
They were caught by surprise because they'd done all this before on a highly successful mission from 1997 called Mars Pathfinder. Its purpose was to demonstrate what was then a radical new concept: a controlled crash landing with an airbag and a fold-up lander inside carrying a small rover. Pathfinder didn't produce a lot of science, but it did prove that the landing system and rover worked on Mars. It worked so well, NASA decided to use the same technology for MER.
Go with what you know. We had a success. Take the drawings off the rack for Pathfinder, build a new set. Except Pathfinder got dinged for not having enough science return. So we're going to up the science return by stuffing a big rover inside of this lander.
MER is the Pathfinder rover on steroids. It has bigger wheels and suspension to handle rougher terrain. It carries all the cameras, radios, antennas, and the computer that runs everything, which on Pathfinder were all part of the lander. Plus the payload of science instruments and the robotic arm, all of which require more power, meaning bigger solar arrays, more electronics, and a heater to keep things warm at night. It's the ultimate off-road, off-Earth mobile science laboratory. And yet, because of space limitations on the launch rocket, this pumped-up rover must fit into the same size package that carried Pathfinder to Mars. And that's a problem. The solution is a complex fold-up rover that will have to unfold itself after a long, cold, rough trip to Mars. And the whole thing weighs 50% more than Pathfinder, which is an even bigger problem. With the airbags struggling to handle the extra weight, it's even more important now to get the best possible performance from the parachute to control the velocity when the lander hits the ground. The first parachute strength tests will tell them where they stand. The chute will be deployed from this giant dart as it's dropped from the helicopter.
We go to these first tests. Beautiful day. We're very confident.
See, that looks really nice to me. Yes.
On Mars, the parachute will open at more than 900 miles per hour. But in the denser atmosphere of Earth, the same stress on the chute can be achieved at a much slower speed.
Here we go, baby. Here we go. Beautiful release.
We have this massive structural failure. The parachute rips apart. And we're all kind of stunned. First the airbags, then the parachute, and it sets in on us that we're going to have to magically find time in our schedule for a redesign cycle and prove that we have the entry, descent, and landing system that will take us to Mars.
All of a sudden, your whole world becomes that tear, that rock. Why did that happen? How do I fix that? What are we going to do? And the whole mission is riding on fixing those kind of problems. It's a terrifying moment, but at the same time, it's exhilarating.
There are moments where there's an at-all-cost component to the effort, and it can get you down. You can find yourself eating a lot, drinking too much, and it's really an important practice to keep on top of the stress. I'm exercising more than I've exercised in my entire life. I'm working out once a day at least, because if I don't, I go crazy.
Landing on Mars has never been easy.
The Russians tried 7 times to land on Mars before we ever did. One spacecraft lasted for a few seconds. All the rest were failures. If it were easy to land on Mars, people would be doing it all the time.
And then in 1975, 2 Viking spacecraft were launched.
Before Pathfinder, the only successful attempts were the Viking landers in the 1970s. It was NASA's golden age, with powered landers, 10 years of development, and 4 times the $800 million budget of MER.
It was $900 million in 1973 dollars, which is $3.5 billion today.
The Viking orbiters produced tens of thousands of pictures, a complete photographic map of the planet. But a primary mission of the landers was to look for signs of life on the surface, and that search came up empty. What Viking did find is a distinctly unfriendly environment for life. 150 below zero at night, very thin atmosphere, no protection from solar radiation, no organic chemicals in the soil, no liquid water. The verdict at the time was that Mars is dead.
The search for life dominated all of the public and governmental interest in the mission. And when life was not found by Viking, then it was a disappointment. And we had no Mars missions for 20 years as a consequence.
This time, the strategy will be different. The dried-up river channels seen from orbit suggest that Mars was not always as barren as it now appears. Scientists can imagine an early Mars where liquid water flowed across the surface, forming lakes and even oceans. On Earth, wherever there's liquid water, there's life, even in the most hostile environments like hot springs, beneath Arctic ice, and deep underground. In the search for life on Mars, NASA's current strategy is to follow the water.
If we can find the places on Mars where water pooled, then that's where you want to go. That's where you want to look for life. So water is, if you will, the scent of the life that we're looking for.
There are many places on Mars that may once have been wet, but only a handful where the rovers can actually go. They're solar powered, so they need to be near the equator where the sun is almost directly overhead. And within this narrow band, they can land only at the lowest elevations, where the parachutes will have enough time in the thin atmosphere to slow the landers before they hit the ground. That eliminates 95% of the planet, and much of what's left is too dangerous for landing or for operating the rovers. After 2 years of investigation, they're down to a small handful of possible landing sites.
All right, we can get started. Right now, we're a week behind in selecting our wind-safe sites, so...
This is where it gets difficult.
Believe me, these sites are not all created equal from a science perspective. Some are very exciting, some much less so. And they're going to be chosen largely on the basis of their safety.
Scientifically, this thing has nothing going for it, so...
You all understand the threat I'm trying to protect us against, right? Which is that we have... There's this natural tension between the scientists and the engineers, because the engineers are the ones who have to tell the scientists the possibility of failure if we do what you want is too high.
One site they can all agree on is called Meridiani Planum. It looks relatively safe, and orbiters have detected a large deposit of the iron mineral gray hematite, which on Earth usually forms in the presence of water. But the scientists want very badly to try something more adventurous for the other rover.
There's a place called Gusev crater, big impact crater, maybe 100 miles or something across, and it's got this huge dried up river valley flowing into it. It's hard to believe that this thing didn't have a great big lake in it at some point in Martian history.
sediments are going to be deposited in that lake, you should have a good sedimentary record of liquid water and whatever was going on there. So Gusev Crater is a fabulous place to go.
But Gusev may have strong winds, and that presents a serious hazard for landing. Just before impact, reverse rockets will fire for a few seconds to reduce velocity to something the airbags can handle. But if the wind is blowing the lander along horizontally relative to the ground, or causing it to swing when the rockets fire, the lander could hit the ground with too much horizontal velocity and potentially disastrous results. The engineers have added another rocket system to counteract some of that sideways velocity. But it may not be enough to handle a worst-case scenario at Gusev Crater.
The engineers know that the science team wants this site, and we want to go where they want to go. But we will not go where it's too dangerous to go.
The final decision will be made at NASA headquarters. But for Gusev to be an option, the engineers will have to get maximum performance from the problematic airbags and parachutes.
We're working nights and weekends to try and get that job done. We're really pushing to try and make this Gusev site work for the scientists.
The airbags have been redesigned with a loose secondary bladder inside. Like the inner tube of a tire, it's isolated from the outer layers, which absorb most of the stress. The new design has survived a series of punishing tests, up to the equivalent of hitting a pile of rocks at 50 miles per hour. This bodes well for the prospects of going to Gusev Crater. But unless the parachute problem can be solved, they won't be going anywhere at all.
Currently, this project does not have a parachute design that works. That's not a good place to be in.
They've moved to the wind tunnel at NASA Ames near San Jose, California. This 135,000 horsepower wind machine will make it possible to test more parachutes in less time than the helicopter method. And time is the enemy.
There's this, sort of point in
Since
here
the
which
failure of the
eventually
first
will
test,
reach height.
the landing team has been searching for ways to make the parachute stronger. Simply using heavier fabric won't do it. There's no more room in the canister for thicker material. And there's no room on the lander for a bigger canister.
Because we can't fit any more parachute, what we have to do is take a smaller parachute. Thicker fabric, but less square yards of fabric.
But this creates problems. If they shrink the diameter too much, there won't be enough drag to slow the lander down. An alternative is to shorten the band. But the band controls stability. If it's too short, it could make the chute more vulnerable to wind. It takes weeks to build a parachute. So with time running out, they've come to the test with several design variations, hoping that one of them will work.
This test is the big deal. If we have a failure here, that's going to start a measure of desperation we never want to find ourselves in. So.
The first chute will be fired from a mortar on top of the tower when the wind is up to speed.
Stand by for drive sync to utility. 4, 3, 2, 1, fire. Get a good deployment. Come on. Come on. Hello. That's strong oscillation on the strut with the...
This was not in the plans.
Al, can you see the parachute on the video?
The chute fails to inflate, a phenomenon known as squidding.
I would initiate a normal stop.
Okay, let's have a drive down stop.
Instead of solving a problem, they've uncovered a new one, and they don't know what's causing it.
I know. It's super, 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 super mega. This is super mega bummer. So, just when we thought we were there, just about to cross the finish line, out of nowhere this thing comes. It certainly was the worst feelings I'd had thus far in the project.
I want to see how stiff, you know, you can see the...
In 30 years of testing this type of chute, from Viking through Pathfinder, squidding has never been seen before.
It looks like we'd expect it to just go now.
Yeah.
Come on, go now. The parachute is displaying that it has a personality disorder. In a situation like this, you need to think about all the possible solutions. And then you have to get moving down all of those solution paths because you don't know which one is going to get you out of the woods.
Okay, I need a favor from you.
They can't prove the strength of the new parachutes until they find and correct the cause of the squidding.
This is a bit of a ghost. By the end of this week, it could be an unpleasant memory, or it could stay with us and be a very, very serious problem that we might not really have a solution for.
And what happens if you don't get a solution for it?
Well, it would be dramatic, but this could be a mission ender.
The next day, the bosses arrive from JPL. They've been through this before, so no one is panicking. Yet.
Every one of our missions seem to have some sort of grand challenge in the final year before launch, as this seems to be part of the deal. I guess it's because we don't do this often enough. It adds to the stress levels, especially since Mars is marching closer and closer. That launch date is coming closer and closer, and we have very little elbow room.
To inflate, a parachute has to trap more air than it lets out. Air flows in from the bottom, and some is allowed to escape through a vent at the top and the gap above the band. But if too much escapes, the chute won't fully inflate. In theory, it's simple, but in practice, parachutes are a nightmare for engineers. The physics of inflation are complex and hard to predict. To figure out what's going on here, they'll have to run some experiments. They start with the simplest possible solution on the failed parachute. They'll make the vent hole smaller and try again to inflate the chute.
Now we've tacked this restrictor inside the vent of the canopy, and I'll lay it out here now.
The chute can't be repacked and fired from the mortar, so they tie it closed at the bottom, crank up the wind, and hope for the best.
Okay, we're at 61 knots, 12Q.
When the tunnel is up to speed, they release the line holding the chute closed.
Pull, Jason.
Line went flat.
Yep.
They taking data?
Yeah. There it is. Test work. How long do you want to hold it? Very interesting. Wait here.
Incredibly, the culprit is exposed on the first try. This parachute was mistakenly built with an oversized vent. Now that the chute is inflated, they can see that the strength problem has been solved. But they're not done yet.
Okay, Cash, let's go to 5.5.
It will take another month of work to arrive at the final design.
2, 1, fire.
Come on. Come on.
Look at that thing fly! Beautiful, absolutely beautiful.
Just days before their deadline, the parachute team has found the ideal combination of strength and stability.
A perfect inflation and a perfect handling of the loads by our most desirable, at a system level, this is our most desirable parachute.
What this means now is that the scientists are going to have a shot of getting to that Gusev crater landing site.
And that's the #1 science site.
Put her there.
The landing site decision is still months away. But the airbags and the parachute are ready for Mars. It's 5 months until launch. The rovers are almost ready to go. The hardware, at least. The software is another story.
The software for launch, cruise, entry, descent, and landing, getting down on the surface, that is in good shape. But the software for driving around on the surface and doing the science is still kind of shaky right now.
There simply isn't enough time to teach the rover everything it needs to know before launch. So they'll keep working on the software and then reprogram the computers by radio when the rovers are on their way to Mars.
You can send the vehicle, and then you can launch the software off into space 6 months later.
The engineers are doing all they can, but soon their rover will be on its own.
I hope it's not a rebellious teenager. And I'm hoping that the environment we put it in challenges it, because that challenges us, but doesn't challenge it too much.
3 months before launch, the rovers are on their way to Kennedy Space Center in Florida. It's the first leg of a journey that will end on Mars. At the launch pad, preparations are underway. The engineers carefully inspect the rovers one last time, and they find a problem. A faulty circuit board inside both rovers. To replace them, they must open the solar panels by firing explosive fasteners called pyros, of which there are dozens on each rover.
The rover solar arrays were already fastened together. Everything was all fastened up tight. We were ready for launch. We had to open them up again. The only way to do it was by actually firing live pyros. Bang, bang, bang.
With the panels open, the problem is easily fixed. New boards go in, the panels are closed up again and secured with fresh pyros. But just 3 weeks before launch, the engineers discover that pyros can sometimes short-circuit when fired. And a short might have overheated components called resistors in the pyro-firing circuits, compromising their ability to fire pyros on Mars.
What we're worried about is the possibility that these resistors could have been heated to the point where they have been destroyed. And next time we use them at Mars, they might not work. And we have no way of getting at them and testing them. The rover is ready to go to the launch pad. It would take weeks to take the thing apart. And it would blow our schedule. We wouldn't be able to launch. This could threaten the whole mission. I mean, these things could, the rovers could end up in the Air and Space Museum over this. Okay, if we're not able to launch these things now, it may not make sense to ever fly them.
The only way to prove that the rovers are okay is to test all the pyros that were ever fired and see if any of them has a short circuit.
If it's not shorted out, pyro's fine. You're ready to fly. If you find that it's got a short circuit in it, then you got trouble.
The problem is, no one expected to need those fired pyros again. Now they have to find them.
And so there was this treasure hunt. And people are going in bags and shelves and pulling things apart. And gradually, piece by piece, they were found. The last one, the critical one that we needed to prove that we were really okay, was found yesterday. 3 days before launch, and we're still sweating these resistors. It was awful.
On June 10th, rover number 1 is finally cleared for launch. And it now has a name, Spirit. The landing team has delivered what the scientists asked for, a system capable of handling Gusev crater. The site chosen for Spirit by NASA Associate Administrator Ed Weiler.
Being the end of the food chain on this thing and being the one, if something goes wrong, is the one ultimately going to have to explain to Congress why it went wrong. You know, that's one of the honors of being an associate administrator. It's a scary mission. There's an awful lot of things that have to work just right. And the entry and the descent and the landing are the ones that really worry me. If we get on Mars and get that thing moving, I think we'll be just fine.
I'm not nervous, man. I'm ready to fly. It's been a long time coming. Today's the day. We're heading to Mars. Maybe today, maybe, you know, a few days, depending on what the weather does to us, but it's time to fly.
CLCDR, LC-17A, launch enable, 100% lock. ATC-3, main power disable on.
I want your keys in the trunk. It's called AAA.
ATC-3, main power disable on. On, 5 seconds.
T-minus 15.
Electronics go. And hydraulics go.
Gotta remember to breathe. Gotta remember to breathe.
T-minus 10, 9, 8, 7, 6, green board, 5, 4, 3, 2, 1. Engine start and liftoff of the Delta II rocket carrying the Spirit from Earth to planet Mars.
Beautiful! Yes! Come on! All right! Come on, baby. Keep going. Look up there.
Jettisoned all 6 solids and we've ignited the other 3. All 3 air starts are up and running, ramping up to their peak thrust. NFC, report spacecraft go.
A month later, it's a night launch for rover number 2, now called Opportunity. A series of problems with the rocket has consumed almost 2 weeks of the launch window. Only 1 week remains, after which Mars will be out of reach for another 2 years. But tonight, everything looks good. Bagpipers from Cornell will provide a musical send-off.
Don't worry, you'll see it. We're just about ready.
35 seconds. Electronics go. Hydraulics go. Pressurizing. 5 mils.
This is it.
Green board here in the mission.
For Steve and his family, it's been a long wait.
Go for launch in 20 seconds.
20 seconds!
15 seconds. Hold. We've had a hold.
Hold. Hold!
We've had a cutoff.
Hold. 15 seconds.
We're going into recycle.
And the clock is stopped.
A glitch in the fuel system stops the countdown. Armed for launch, the rocket is now literally a bomb.
Prop 1, secure water flow. Closed. Prop 2, PSD purge, press closed. Closed. Hydraulic external power off. Off.
Over several very long minutes, the launch crew manages to pull it back from the brink.
7 seconds.
The fuel problem is also resolved, and a half hour later, they're ready to try again.
You know, I was so sure last time. I don't know what to think this time.
Yeah, right.
T-minus 10.
10, 9,
8, 7, 6, 5, 4.
Here we go.
3, 2.
Here we go.
Main
There we
engine
go.
start.
God.
0 and liftoff of the Delta rocket with Opportunity.
Come on, baby. Listen for it. It's hard to say goodbye. I'll see him again in pictures, but I'm never going to lay my eyes on it again. But hey, they got to do what they got to do.
Seven months later, it's landing day, January 3rd, 2004. The rover's Spirit is due to touch down in Gusev crater at 8:35 p.m. Pacific Time. In mission control at JPL, the landing team braces for the most dangerous 6 minutes of the journey.
We're landing on Mars. You know, the thing's 100 million miles away. 2/3 of the spacecraft that have ever gone there have died. So yeah, it's dangerous.
The team has worked very, very hard. And there have been some fairly significant sacrifices. And so we're really hoping for a payoff.
Flight MTS Mach.
At 8:14 p.m., they pick up a faint signal that the landing capsule has separated from the cruise stage. As the animation shows, the rover is now on its own.
Copy that.
And the mission controllers are just spectators.
3, 2, 1.
At 8:29, the capsule hits the top of the atmosphere. A few minutes later, the parachute opens. The lander separates.
Radar is working.
Airbags inflate. Rockets fire. And the lander is cut loose.
So roughly any signal that we receive from now indicates the vehicle would be alive, on the ground, and bouncing. Stand by.
Now they wait for a sign that the rover has survived.
What do we see?
But suddenly, the signal is gone.
We saw an intermittent signal that indicated we were bouncing. However, we currently do not have signal from the spacecraft.
Minutes pass. Finally, at 8:51, Spirit calls home.
It's an amazing night, man. If things go well, we're going to see Gusev Crater, our new home, in just a couple of hours.
Just hours after landing, Spirit is not only safe on Mars, it's hard at work, sending home pictures. Within days, the high-resolution camera sends back the first color postcard of the Martian landscape. A new era of exploration has begun. Welcome to Mars.
Nova is a production of WGBH Boston.